All right, hey, it's Robert Cooper again for data visualization. This time we're going to talk about some geoms, and I'm going to do some quick examples of a bunch of different kinds of geoms. I'm calling this video various geoms. Let's see, I'm going to load the tidyverse, which I've already done. It's always good to clear your plotting environment before you start a session, and also in between plots if you're doing a lot of plotting. Dev.off is a good way to do that. I've already done this, which is why it's clear to the right. But if you do that, you'll have an easier time usually executing some of your plots. All right, I'm going to use two data sets. I'm going to use the data diamonds, the diamonds database, which is base R. We run this and we look at it, and it's got a bunch of observations in it, and it has these diamonds by carat, cut, color, clarity, price, and some physical features about the volume, the length, width, depth, that kind of stuff. All right. And then I'm going to use a movies database from the IMDb database that is enormous as well, and it has lots of different variables. IMDb score is sort of the main dependent variable, maybe also gross, which is the earnings at the time of the pull, the database pull. There are all these other interesting variables that I'm not going to talk about now. Anyway, and so we're going to just introduce a bunch of geoms. Plots included will be bar plots, box plots, dot plots, violin plots, histograms, density plots, two-dimensional density plots, two-dimensional histograms, and hex bin plots. In the next video, in one of the next videos, I'll do point range plots and error bars, which are really good if you're doing data analysis and you've run some models, you have some point estimates, and you want to put confidence intervals around them and then show those visually. That's what a point range especially is really good for. Error bar is okay. I kind of prefer the point range. Plots not appearing in this film include pie charts, ternary plots, bag plots. Now, I will show you how to do a pie chart reluctantly. The last I looked, ternary plots and ggtern weren't working very well, so we're not going to actually use that. And plus, they're not that great. Bag plots are just terrible, so we're not even going to worry about that. Why not pie charts? Pie charts are normally not good. They're only good when you have few categories and large differences between those categories. The human eye is really bad at distinguishing between similar sized pieces of pie, but it's really good at looking at two bars and looking at which is either longer or taller. Bar plots are fundamentally sound and pretty hard to beat when it comes to categorical variables. So when is a bar plot good? It's good when you are displaying by categories. Now we can do that by a count, or we can do that by some estimated statistic or something that's already in the data. And I'm going to show you how to do both using the diamonds data set. We're going to go diamonds, and then I'm going to do cut as the categorical variable. And I'm also going to set it as a fill aesthetic so we get some color. But that's all I'm going to put in, and then I'm going to go geom bar, and this is going to be a count of the observations by each category of cut of diamonds. All right, and here's what it looks like. Obviously, there are things that we need to fix, like I would change the theme. I would actually get rid of the legend because it's redundant, because all that information is in the x-axis and the colors themselves, so we wouldn't need it. There's a lot to change, but we're just going to keep it base for now, just to get you through and so you can see what it's like. Now, in order to do a bar plot that isn't just a count, that is in fact either something in the data that is maybe continuous or something that you estimate, we need to change up with either geom bar, and we change the stat to what's called stat equals identity. Normally it is stat equals bin, which is just the count cases form. We don't want to just count cases this time, because what I'm going to do is I'm going to group by cut, and I'm going to summarize and get the mean carat. And this is a weight measurement. Okay. So we're going to be able to group by cut, summarize, get the mean of carat, and then we're going to go stat equals identity. And now we're going to be able to run this. And you can see the average carat size or weight is larger the less ideal the cut, or the more ideal the cut, the lighter the weight of the diamond. That would make some sense. Equivalent to geom bar stat equals identity is geom col or geom column. This is identical to what's before. It's just geom col versus geom bar stat equals identity. Okay. Box plots. Box plots show continuous variables by different categories, and they show you mean, max, outliers, and interquartile range, like so. So a box plot wouldn't be best for diamonds here because look at all the outliers, especially on the high end. That kind of makes sense. I think this is good enough. So let's move on to dot plots. Dot plots are similar, but what they do is they take the continuous variable on the y-axis and they actually cut it into bins. In this case, it's going to be one observation because I'm going to add a third variable here. So I'm doing a group by, but this time I'm doing by group by cut and color of the diamond. Then I'm summarizing and I'm getting mean carat size, so average carat size. And then I'm going x equals cut, just like before. Y is mean carat, and then fill is color. So the actual dots are going to be different colors by the color category. And then we do geom dot plot. And bin axis, it means which axis is the one that's getting binned from continuous to non-continuous. Okay, so it's kind of a histogram cousin in that case. And then stack direction, I'm going to have it centered. And then you play with bin width the way you will with histograms. Okay, I played around with this and found a level that I thought looked pretty good. So we're going to run it. It's going to look like this. And so you've got average carat on the y-axis, and you've got cut on the x-axis, and you've got color as the fill. So you've got 3 dimensions going on here in this 2-dimensional plot. All right, moving on. Violin plot. Violin plot is similar to a box plot, but it shows as a density curve. It's a symmetrical density curve, essentially. So it's x, y, and I'm keeping the fill for the different colors. But you don't need that. You would need an x and a y to execute it. Okay, so it's kind of like a density plot for carat by categories of cut, if that makes sense. Again, the legend is redundant, so we want to get rid of that. We want to clean up all sorts of things, but that's not what this particular video is about. Okay, moving on to histograms. Let's do a histogram. Continuous variables cut into bins. So you have a single variable, you cut it into bins, and you show it. This is the cousin to the density plot. We're going to run it. Again, I didn't add any color this time. I just did carat just to see what the distribution would look like. I played with the bin number, so you can see if I move it to 30 bins, what it would look like. It'll look a little different, right? You really want to look at bins when you're using a histogram to see which one kind of shows the right amount of variation to tell the right story. The right accurate story, I should say. All right, moving on to a density plot. This is a continuous variable with a smooth density plot. So it's basically like taking a histogram and putting a smoother curve over it. Right? So we're going to use carat again. I'm going to put in a fill color blue. I'm not putting it in the aesthetic because it's not attached to a variable. And it's going to look something like this. It obviously looks very similar to these two histograms, as you can see, as it should. All right. You can actually cut this into, we could actually do fill equals cut instead. This is kind of coding this on the fly, but we could change this and we could do different density curves. Well, right now it is stacked. This is a stacked density curve where it's cut up by the different levels of cut of diamonds. Okay, so we could also change that and make them overlap, and then reduce the or increase the transparency by reducing what's called the alpha, and then they would overlap, and you'd be able to see the density plots of all those. But we're not going to do that right now. That's a density plot, a two-dimensional density plot. This is pretty useful when you're trying to look at the total distribution of two continuous variables, that especially if you have a lot of observations and hopefully you have a bunch of variation in them. It's not like a very clear relationship or a almost perfect relationship. Right? Okay. So this is kind of what they look like. They kind of look like elevation maps, right? And you usually have to play with the level and or fix the legend, because the legend is usually not very informative on its own, at least in its original raw state. So what we did here, I moved on to the movies database, and I used X is the log of gross earnings and Y is the IMDb score to see if there is a relationship between those two continuous variables. Why did I log it? Because there are some crazy outliers. So just to pull the distribution back a little bit towards a normal distribution, still monotonic transformation, so it's okay. And then we use this geom density. In this case, I did filled. The filled is the reason why these levels are filled with color. Okay, this is actually a new update to ggplot2 as of the middle of 2020. Until recently, you would use an argument inside geom density 2D to do this. All right, moving on to a 2D histogram. This time I'm going to do the log of the budget against the IMDb score to see if budget has anything to do, if there's any relationship in the movies database. I'm going to do geom, and this one's called geom bin 2D. Again, play with the bins when you're working with histograms, and this is just a two-dimensional histogram. And we'd want to play with some stuff, but it looks kind of interesting. I don't know. I kind of like the density plot better. These are almost redundant, right? You're choosing between which one between a density and a histogram would actually look good here. This has kind of a weird Minecraft look to it, right? Which can be good. You can change the number of bins, and you can see the difference, right? That actually produces a weird stripe here, so you definitely wouldn't want to do that. Let's go down to 50 and see what it looks like. Yeah, back to something like that. That's fine. Alrighty, and this is just a different variation. I have no reason why I left that there. And the final one I'm going to show is going to be a hex bin. Hex bin is very similar, but the bin is shaped like a hexagon. It's a hexagonal. So it really just looks a little bit different, but it's doing the same thing. So you see it's got a honeycomb effect, which, again, it is sort of a hexagonal shaped two-dimensional histogram, if you will. So play with the bins. But it ends up looking something like this. And again, as always, this is just the beginning of producing a good plot like this. You would always want to clean up your labels, potentially move the legend, change. You could change every detail possible, pretty much with theme. We would want to potentially change our own colors through. We would use a scale if we had a legend, and you would use hex codes, hopefully, because you have, in a computer, in hex code, you have almost 17 million different variations in color, so there's no reason for you to have bad colors in a plot. especially if you know anything about colors. And I know that I have at least 3 videos up on data visualization for color theory. So I have certainly waxed nerdy and poetic about that already. I will probably continue to do so in the future, and you should make sure and check those out so you can make sure your colors are also tight when it comes to your plots. All right, so in the next video, I'm going to do a brief video on a geom, point range, and error bar, and I'll see you on the flip side.